Good morning. Welcome to the lecture series on digital electronics. In today's lecture, we'll look at how to simplify Boolean expressions by using a method called Karnaugh map method. So previously we have seen how to simplify Boolean expression using theorems and laws. But as you see, when we want to simplify using a Boolean expression using theorems and laws, there is no particular procedure that one has to follow. We are not having any clarity that what is the next steps to be followed after each step of simplification. So here the Karnaugh's map method gives a solution for this and provides a systematic method for simplification, and also to express the Boolean expression in a different form other than what we started with. So basically, this simplification of Boolean expression is carried out to reduce the number of variables and the number of operations, or I can say to reduce the number of literals and the number of operations that are involved in the expression. So what will happen if we reduce the number of operations or the number of variables? So when we try to reduce the number of operations or the number of literals, where a literal is a variable in its original form or complement form. So when we try to reduce the number of literals or the number of operations in a Boolean expression, that we are actually reducing the number of logic gates required to realize the function, are required to construct the logical circuit diagram. So if a logical circuit diagram contains a less number of or minimal number of logic gates, then the circuit is considered economical. So we'll try to simplify the Boolean expressions. So here we follow a method called Karnaugh method, which gives us a systematic method for simplification of the Boolean expression. So but to use the Karnaugh map method, we require the Boolean expression to be given in the standard sum of products form or provided in the standard product of sums form. So even though the expression is not given as standard sum of products, we have to first convert it to standard sum of products form or standard product of sums form. Then only you can use that expression for further simplification by using Karnaugh's map. So before going to actual simplification method, we'll discuss the basics of the Karnaugh's map. So Karnaugh map, in short, it is called as K map. It's a diagram consisting of squares, a number of squares. So the number of squares, then how many number of squares the Karnaugh map contains? The Karnaugh map contains 2 power n number of squares when you want to represent an n variable function. That means to simplify or to manipulate an n variable function, you require a Karnaugh map which should contain 2 power n squares. And squares sometimes here they are also called cells of the K map. So I require 2 power n cells for a n variable function. So a K map containing 2 power n cells is called n variable K map. So then what each cell or square represents, or what it mean, or what each cell is meant for with respect to the function. So here each cell represents either a minter or max term for an n variable function. So if you take an n variable function, there will be 2 power n minterms and 2 power n max terms. So here the K map also has the 2 power n squares corresponding to a minterm or max term of the function. So when we want to simplify a Boolean expression given in the standard sum of product form, we'll treat each cell representing a minterm of the invariable function. And similarly, when the Boolean expression is given in the product of sums form, standard product of sums form, then each cell is treated to represent a max term, the general max term of the n variable function. So any n variable function you can take expressed in the standard sum of product form can be represented using K-map, because that function, when it is expressed as standard sum of products, it is expressed as actually the sum of minterms. So anyway, the K-map gives you the total number of minterms present for an n variable K-map. So to represent an n variable function which contains some of those minterms, you can select the squares corresponding to the minterms present in the function. So we'll look at all these concepts by going through examples. So but before going to anything further, just we review this, that here we are using a map called, or a diagram called K-map, which contains a 2 power n number of squares corresponding to an n variable K-map, or to represent an n variable function, where each cell represents a minterm or max term when the function is expressed in standard sum of products or standard product of sums form. And this K-map uses certain properties and can be used to simplify a given Boolean expression or to write an alternate expression for the given Boolean expression. So since we are saying that the K-map or the Karnaugh map is a diagram containing the number of cells, say 2 power n, that means it is depending on the number of variables of the function. So there will be there we have to construct the k map, different k maps for different variable function. So we'll try to see how a k map can be constructed for a 2 variable function, or for a 3 variable function, and for 4 variable function separately. So first we'll look at how a 2 variable k map is constructed, and how a function of 2 variables expressed in standard sum of product form can be represented on the k map. And next we'll look at the other variable k maps. So first we'll go through the 2 variable k map. So if I assume that the 2 variable k map can be used to represent and to simplify a 2 variable Boolean expression. So if I assume that the variables of the function are a comma b, the Boolean variables on which the function depends are a comma b, then k map, so it's a 2 variable function, so the number of variables here it is 2, then number of cells equals 2 more 2, which is 4. So the number of cells must be 4 present in a k map. So here we'll draw a k map, and we'll draw 4 squares corresponding to 4 minterms of the 2 variable function. So number of variables are 2, number of cells must be 4, as the number of minterms are 4. And here you can see we have drawn the Karnaugh map with 4 squares corresponding to 4 minterms of 2 variable function, assuming the variables are a comma b. So here so we said that each square corresponds to one minterm of the function. So then which square represents which minterm? So to decide that, we here see that there are 2 rows and 2 columns, and we assign a variable for the rows, and we assign one more remaining variable for the columns. And here we assume that we assign the first row, we say the first row corresponds to the variable a when its value is 0. That is, when its value is 0, since we are representing the minterms, when the value of a is 0, a is represented in its complement form a bar. So similarly, in the second row, so the rows are represented by using variable, and the variable a has the 2 choices, either it can be 0 or it can be 1. So when it is 0, we say that it represents row 1. So when it is 0, a is represented in its complement form, as we are dealing with minterms as standard products. And the second row, the other value that a can take is a equal to 1. So when a equal to 1, a is represented in its original form. Similarly, when you look at the columns, we have two columns here, and the variable b represents the two columns. But when b can assume either 0 or 1. So when b assumes 0, we say its value it can be represented as b bar. So we say that the first column is represented with b bar. And similarly, when b takes a value of 1, then it is represented with its original form, then it represents the second column. And now you can see, so there are 4 cells, 1, 2, 3, 4, and you can see that this cell represents general minterm of two variables. The minterm, a standard product, can be obtained by combining its row variable first with column variable. So row variable is a bar and column variable is b bar. It is a bar dot b bar actually, so it's a standard product. So variables are combined by using AND operation. Similarly, this cell represents a minterm. How to get minterm? Row variable combined with column variable. So it is a bar b, and this it is a b bar, and this it is a b. Now you can see that the two variable came up. So since there are two variables and each variable can take either a value of 0 or 1, 0 or 1, and so since we got the two rows and two columns, and we say assume that the a represents the rows and b represents the columns, and since a can take two values, we say that the when a equal to 0, it represents the first row, a equal to 1, it represents second row, and here we say that b also, when it is 0, represents the first column, and b equal to 1 represents the second column. And by this we would be able to write the minterm represented by each cell. And similarly, we have seen that there is a notation for each minterm. It can be represented with m, small m, followed by a subscript which gives the decimal representation, decimal equivalent of the corresponding binary. So here we can represent this in an alternate way. That the 4 cells corresponding to the 4 minterms, and here you can see that this cell, I can say that corresponds to minterm m0, where m represents a minterm and the 0 is the decimal equivalent of this binary. Since a bar means its value is 0, b bar is 0, 0, 0 is m0. Similarly, this one is m1 and this one is m2 and this is m3. So this is an alternate short way of representing the minterms on a K-map. Or I can show here this value of a is 0 here for this row, and for this row it is 1, for this column value of b is 0, and for this it is 1. And here you can see that This is m0, m1, m2 and m3. Looks like we have followed the decimal sequence, but this is not the case actually, so that we'll see later why the sequence will not follow the decimal, that is m0, m1, m2, m3. So next we'll look at how to represent a two variable Boolean expression using a K-map. So here we assume the function f equals a plus b. F equals a plus b. So this function we have to represent on the K-map. So we already learned that to represent a function using a K-map, the function is either is to be in to be expressed as the standard sum of products, that is each product term must be standard product, or each term must be min term. And here you can see that there are two terms, neither of them is a standard product or a min term. So when a function is expressed this way, and to convert this into standard sum of product expression, we have seen already what is the method, and that method we have discussed in the previous lectures, that what we have to do. So since it is a two variable function, this can also be written as f of ab, a function of two variables. So for each product term we have to multiply with the missing variable or with its complement. So for this a product term, the missing variable is b. So multiply this a with b plus b bar. And similarly, plus for this product term, what is missing is a. So multiply it with a plus a bar. So what you will get, it is ab plus ab bar plus ab plus a bar b. So what you have to do, so this term got repeated, so remove the repeated one. It is ab bar plus a bar b. So now you can see that this is a function containing three standard products. So now this is in the form of standard sum of product form. So we'll see how to represent this on like two variable K-map. So we got the expression f equals ab plus a bar b plus ab bar. So then how to represent this function? So first what you have to do is to construct a two variable K-map. Construct a two variable K-map, so make four squares and here you can see that so what are all the min terms the function contains is ab. First one is ab. So where is the cell corresponding to the min term ab? here you can see this represents a bar, this is a, and this column b bar, and this is b. Now when you write this way, you can see that this cell represents ab, and to show that the function contains this minterm, what you have to do is just enter a 1 into the cell corresponding to the minterm present in the function. Similarly, also enter the other minterms that the function contains on K-map. So a bar b, so this is a bar first row, a bar b means first row second column, so enter a 1 into this, and next last one is a bar, a b bar. A b bar means a for the second row, b bar is for the first column. So this cell represents the third minterm, a b bar. So this is how we represent a function using K-map. So now here we'll see one thing. So we entered the function here. Then how to simplify the function? And here we'll see how the properties of K-map can be used for simplification of the function. When I represent the function in this way, here you can see that we have represented the minterms of the function by entering 1 into the corresponding cells. And now we have to look at the cells which are containing ones, and in order to simplify, we have to group the cells containing 1. But how to group the cells? For example, we can group only adjacent cells. So we can group only adjacent cells. But what is meant by adjacent cell in a K-map? So for example, if I consider this cell, for this cell is considered adjacent, and this cell is also considered adjacent, but not this. So this is adjacent, this is adjacent for this cell. So for this is adjacent cell, and this is also adjacent, but not this one. So how we are saying that this cell is adjacent and this cell is also adjacent, but not this? Because when you are moving from this cell to that cell, this is what we are saying as adjacent cell. You can see that there is a change in only one variable. So this is corresponding to the minterm AB bar, and this cell corresponds to the minterm A bar B bar. And when I moving from this cell to this cell, there is a change in only one variable A. It is changing from A to R. So this cell is considered adjacent to this. Similarly, when I move from this to this, the variable A is same, but the B variable changes from B bar to B. But why I am not considering this cell as adjacent to this? You can see that this cell represents AB bar, but this cell represents A bar B, and you can see that when you are moving from this to this cell, you can see that there is a change in the two variables. There is a change in the two variables. A is changing from A to A bar, and B is changing from B bar to B. So since there is a change in the two variables, I do not consider this cell adjacent to this. So what I can say in another way, that the cells which are diagonal to each other may not be considered, are not considered adjacent cells, and the cells which are differing in only one variable are considered adjacent, and the cells which are adjacent are the, if they contain ones, and those ones can be grouped. So for example, these two cells are adjacent, and also say that for this is also adjacent, but you can see that there is no one in the cell, so no need of grouping this cell. So we'll try to group the cells which contains the ones entered. So if we want to group these two cells which contains ones and which are also adjacent, you can see that it results in a product term. So what these two cells actually represent? These two cells represent A B bar and A B, and I can say that by grouping, I mean that I am logically adding the two terms. So when I group these two terms, or these two cells containing ones, that results in a product term which eliminates the variable which is changing from one cell to other cell. So that is, it results in a product term which eliminates the changing variable, and here the changing variable is B. It changes from B bar to B. So what remains is the product term, resulting product term is A only. So when I group these two min terms, it results in a product term A. It results in a product term which eliminates the variable which is changing from one term to other term, or one cell to other adjacent cell. So this way, when I combine the two adjacent squares, I am eliminating the variable which is changing, and the resultant product term contains less number of variables, and this is called adjacent cell property of the K-map. And this property of the K-map will be used to simplify the Boolean expressions. So there is, and this is how we reduce or simplify the Boolean expression. So far we have discussed only the case of a two variable K-map. Now we will look at the three variable K-map. Three variable K-map. As we know, the number of variables are here. Number of variables equal to 3, and I say that the number of min terms present for this three variable function is 2 power 3, that is 8. So the number of cells in this K map must be 2 power 3, that is, it must be 8. So this K-map should contain 8 number of cells, and one way of drawing this K-map is 2 rows and 4 columns. And draw 2 rows and 4 columns, and I will be able to get 8 number of squares. And if I assume that the variables of the function are comma b comma c, then I use the first variable a to represent the rows, where the value of a is 0 for the first row and value is 1 for the second row, and the remaining two variables are used to represent the 4 columns. And here the two variables b, c represent the 4 columns, and then so that means bc can take can have 4 combinations, that is, both of them can be 0, both of them can be 1, and one of them can be 0, other will be 1, and vice versa. So there will be 4 combinations will get, and those 4 combinations will represent the 4 columns. So then what is the sequence followed to represent these 4 columns is, the first column is represented with b bar c bar, that means when both b and c assume 0, or b and c take 0. The second one column is represented by variables b, p bar, c, and you can see that whenever we want to represent, there must be, when we are going from one column to the other column, only one variable has to change. And here you can see that b bar, c bar, b bar remains same, only c is changing. And when I want to represent the variable for the next column, you can see only one variable has to change, that means it is, you can write it as b, c. So from this, b remain as it is, c has changed. From this, c will remain as is, b will change. And after this, b remain as it is, c will change to represent the last column. That means you can see that now you can see this how we represented. So b bar, c bar, so it's a 0 0 0 1 0 0 0 1, only one bit change. From 0 1 to, you cannot write 1 0 because both bits will change. So 0 1 2, we will say that 1 1, only one bit change, and 1 1 2 again 1 0, again one bit change. So the values of variables must change in only one bit when we are moving from one column to the next column. And this is the sequence that is used when we want to assign variables for the columns. And you can see that in this cell now we got 8 cells. This cell represents the minterm a bar, b bar, c bar, and similarly this one a bar, b bar, c, this is a bar, b, c, this is a bar, b, c bar, B bar C bar, and this is A B bar C, and this is A B C, this is A B C bar. So this is how a 3-variable key map will be constructed. And now we look at, you can see the alternate representation as short way of representing variables is, so we say that it is ABC 3, so this is M0, M1, and this cell represent not M2 but it is 0 1 1, so it represents M3, and this is represents M2, this is M4, M5, and M7 and M6. So 8 cells and the corresponding minterms are shown in the key map. So now we look at how we can enter a function into the key map and how to simplify the function. So the example function taken here is f equals a bar bc plus a bar b c bar plus a b bar c bar plus a b bar c. So here you can see that the function is expressed as standard sum of products, that you can see that each product term is actually a min term, and you can see that the function is actually of 3 variables and each product term is actually a min term. So we are directly given with the function already present in standard sum of products, so you can directly enter the function into the key map. So for this I draw the key map. See that this row presented by the 2 variables a, b, c. Now we can start entering the minterms into the k map. So the first is a bar bc. So here you can write this represents a bar, this is b bar c bar, this is bc bar, offset, so b bar c, so bc, and this is bc bar. So a bar bc, so a bar correspond to first row, bc correspond to third column. So 1 must be entered into the cell corresponding to a bar bc. Similarly, a bar bc bar, a bar bc bar, this column, this cell, and a b bar c bar, a b bar, a means second row, b bar c bar, first column, a b bar c, a b bar c, so this cell. So 4 minterms we entered once into the 4 corresponding cells. This is how we enter the function into the k map. Then to simplify the function entered into the k map. So how we can simplify the function? Again we have to use the adjacent cell property of the k map, and here you can see that we have 4 cells containing ones. So we have to group the cells which are containing the ones such that the cells are adjacent to each other. So here you can see that for this one, for this cell, this is the only adjacent cell which contains 1. So that means we can group these two cells, and we can combine these two minterms, which results in a single minterm, single product term. And you can see that when I group these two minterms, you can see that this cell represents minterm A, B bar, C bar. So when I group means I am actually ORing or logically adding, and when I group this I am grouping this minterm with this one. So that means this minterm is A, B bar, C. And you can see that the variable, so when I group, I already said that when I group this way the adjacent cells, it eliminates the variable which changes from one cell to other cell. So here you can see that what is the variable that is changing is C. It is changing from C bar to C. So this eliminates that variable, giving us the product term, giving us the term A B bar. Similarly, so I finished grouping these minterms. So if I observe the other cells containing ones, you can see that there is a one here, there is a one here, and you can see that they are adjacent because there is only one variable change from this to this. A is same, C is changing from C to C bar. So I can group these two minterms which represents A bar BC plus A bar B C bar, and you can see that the variable which is changing from between the cells is C, so it can be eliminated, and resulting in, so this pair represents a term A B bar, this pair represents a term A bar B. So there are no more cells which contains ones that are to be grouped. So that means we have finished our simplification process. We have finished the grouping of the cells. So, and in order to complete the simplification process, what we have to do? We have to logically add the resulting terms which we have obtained by grouping the cells containing ones. So logically, so what is the term obtained by first group? Say A bar, and by second group it is A bar B. So we have to logically add the terms obtained, and this Boolean expression, I say that it is a simplified expression of the original the given Boolean expression. So if you see what we did, actually we have taken the given Boolean expression and we examined that whether it contains, whether the expression is in the form of standard sum of products or it is in the form of sum of minterms or not. So actually the given expression is in sum of minterms, so here there is no problem, but if it is not there, we should convert it first into the standard sum of products, the sum of minterms form. So once we get the expression which contains the sum of minterms form, so now construct the corresponding variable keyman. Here it is a 3 variable keyman, and start entering a 1 into the cells corresponding to the minterms present in the function. So we entered ones into the 4 cells corresponding to the 4 minterms of the function, and after entering the ones, we try to observe and try to find out the adjacent cells which contains ones. So here we find one pair of adjacent cells which contains ones, which contains the minterms of the function. So when I group these two minterms, It results in a product term which eliminates the variable which is changing between these two cells. That is, see here, see here. So it results in a product term a b bar. And similarly, when I look at the remaining minterms, so these two minterms are also adjacent and forms a pair. So by eliminating the variable c here and resulting in a product term a bar b. So to get a final simplified expression, I have to logically add the terms obtained by grouping the minterms. So f equals ab bar plus a bar b. So look at some more examples on how to simplify the Boolean expression by using Karnaugh's map in the next lecture. Thank you.